to the where it says Math 125, Summer 2013 on the left.
Right there?
Yeah, and just click that.
Okay.
And then from there, the homework, or you can just click Chapter 11 homework right there.
Okay.
And then just click on the first problem and a window will come up.
It looks like there's an X by question 1 already. Should I do question 2?
No, question 1's alright, because you can do it similar problems until you get full credit.
Okay. So is this Calc 101 pretty much?
Yeah, essentially it is.
Okay. I'm going to shut my camera down. For some reason, my computer, after about 15 minutes on this, starts getting overloaded. Okay, what have we got here? Limit of f of x is equal to 4 as x approaches 7 from the left. But the limit of f of x is equal to 4, but f of 7 equals minus 4 as it approaches 7 from the right. So what can you say about the limit of f of x as it approaches 7? What is it equal to?
So I've actually never even dealt with these. So like this is all Russian to me.
Okay, let me draw something here that'll help. Let's plot this function.
I'm missing the top of the function there.
Okay, I'll move it down here in a moment. Can you see it all now?
Yeah.
Okay. When we talk about limits approaching from the right or the left, what is the limit of y as x approaches 0 from the right? So when we're approaching it from the right, we're coming in on it from that direction. So if I don't get to 0, but as I approach 0, what is happening to y?
It's getting smaller.
No, y.
No, it's getting bigger.
Right. So approached from the right, it's going to positive infinity. If we approach it from the left, what happens to y?
It goes smaller.
It's going to negative infinity. Well, in order for a limit to exist at a number, it has to have the same limit approaching from the left as it has approaching from the right. And in this case, it's not. One is positive infinity, one is negative infinity. So if I said, what is the limit at 0, it would be, it does not exist. Because the very first rule is the limit from the left has to be equal to the limit from the right for a limit to exist at that number. Okay. Another example, let's look at a piecemeal type function. Something like the following. This is more of the classic that they usually use. Let's say we have a hole right there. So at 3, the value of y is 4. So if I have this function here, as we approach, what is the limit? We'll call this function f of x. What is the limit of f of x as we approach 3 from the right?
3 from the right, so you're going left?
Correct. In other words, I'm approaching that number from the right side of the curve.
So it would equal to?
Okay. And what is the limit as we approach 3 from the left?
3 from the left would be 2 again.
So the limit of this function at 3 is what?
2.
Correct. However, what is f of 3 equal to? 4.
4.
In other words, this black dot is the only time that this function is, it's only at 3 that f of x is 4. Every other place, it's approaching 2. So the limit at 3 is 2, even though the value of the function at 3 is actually 4. So that's kind of a counterintuitive concept. But a couple things come out of that. Number one is that limits have to be the same from the left and the right. So let's go back and look at your problem. So we've got the limit as we approach from the left is 4. From the right is 4. But the value at 7 is negative 4. So what can I say about the limit of f of x as x approaches 7? Is it going to be 4 or negative 4?
It would be 4.
Correct. How do we go on to the next one?
Yeah, you just do check answer.
Now, does it put 2 up automatically, or do I have to click on it?
You have to click it.
Okay. Can you see this? Because I might be able to increase the size of this thing a little bit. What happens if I go full screen here? Doesn't change the size. Is there a way for me to blow this up?
I'm not sure. I'm only getting like the very bottom right of the actual problem.
Okay. Is that better?
Yeah, that is.
Okay, I'll leave it like that because it didn't accomplish what I was trying to accomplish, which was to make this bigger. Can you read this okay?
If you slide it to the right.
Slide what to the right?
The whole window.
Ah. Yeah, that doesn't increase the size of the print. Ah, here's a magnifying glass right here. Oh no, that just blows up the graph.
Well, I have your screen full screen for me.
Okay. As long as you can read it, that's what's important. I can read it fine.
Yeah, I can too, as long as you just take the whole window and slide to the right, because I only have half of the problem.
Okay, did that solve that problem right there?
No, you have to drag it from the top.
Oh, so what I did was widen the window. No.
Correct.
So you need me to expand it full screen. Does that work?
No, I'm still only getting half of the problem.
The last time you said that, when I reduced it, that solved the problem. Can you see it now?
No.
This is weird.
I like my screen, I only have a portion of your full screen.
Okay. Which way do
now
I need to move this window for it to be in your view?
Now just up, that's it.
Just up, okay. Does that do it? Is that enough?
Yeah, it's perfect.
Okay. I'll try to leave it in this position, and if anything, you can't see anything, say something. Okay, so
Okay.
use the graph to find the following limits and function value for each value of a. So what is the limit of f of x as x approaches a from the left? Where is a? I don't see it.
A equals 1, it says.
Oh, for a equal 1 and then for a equal 3. Okay, so in the first case, this is a. So what is it as we approach 1 from the left?
Would it just be 1?
Well, we would have to find the curve that we can come in from the left on. So it would be this one here. So we're going to approach 1 from the left. It goes to 0.
Okay.
Okay? Kind of think of it as just following a path. And you have to start away from your final destination, and you want to start from the left side of it and then hone in on it. Whatever number you're honing in on, that's the limit.
Okay.
Okay? So, should we do all 4 of these first? Yeah. What's the limit as we approach 1 from the right?
-2.
What's the limit as we approach 1?
From which direction?
Well, it's not from either direction. In other words, remember for this, well, for this to exist even, the limit from the left has to equal the limit from the right. And in this case, it did not. This limit was 0. This limit was -2. Since they're not the same, this limit does not exist.
Okay.
And what is f of a?
-1.
Okay. And now let's use an a of 3. You'll have to show me how we want to answer all of these, but let's use an a of 3 and answer the same question. An a of 3 would be right there, where my cursor is pointed. So what's the limit as we approach 3 from the left?
1
-1.
or zeros?
-1. It's right where my cursor. Can you see the point on my cursor?
Yeah.
Okay, that's -1 on the y-axis. In other words, we're approaching x. We're approaching 3 on the x-axis. So 3 on the x-axis is right there. So I got to go to my function and approach this point that I'm pointing at from the left. So it's pointing at -1 on the y-axis.
Okay.
So that's that limit. And now if I approach it from the right, what is it?
Would it be? It wouldn't be -1 again, would it?
Yes, it would be.
Okay.
Both of them point to -1, regardless of whether you come from the left or you come from the right.
And so when you're coming from the right,
Then I go up to a point like that, and I come in on it like that.
so then for the other one,
And then the other one, I go a point to the left, and I come in on it like that.
and it doesn't matter if the line actually physically intersects at -1.
No, not at all. No. In fact, this is very normal for a function. The abnormal case was when a was equal to 1. A equal to 1 is the only place on this function where it's not continuous. Whereas when a is equal to 3, we have continuity on the function. It's just a straight line that goes through that. In other words, the limit from the left is the same as the limit from the right. So what is the limit of f of x as x approaches 3?
-1.
And what is f of 3?
F of 3, is that still -1?
Yes. In this case, all 4 of them were the same. They're all -1. because it's continuous. If you have a continuous function, it's always going to be the same. It's only going to produce these kind of problems that we had when a was equal to 1 at points of discontinuity. Discontinuity being where you have to pick your pencil up to draw it. It's one definition of continuity. If I can draw the function without picking my pencil up, it's continuous. Okay, so let's see. We want to check the correct choice and fill in. So the limit of f of x as we approach 1 from the left was 0. And b was...
you have to hit check answer. It does it step by step.
Okay. So the limit of f of x as we approached it from the right was -2. And the limit does not exist as we approach 1 because you don't know whether you're coming from the left or the right. So there's no way we would be able to pick a number. And f of 1 was -1. And 3 from the left, these are all -1. So one row is x values, the next row is y values. So as we hone in on the number 6 on the x, what are we honing in on the y?
9.
Yeah. Okay, the limit of f of x is 10 as we approach 5. The limit of g of x is 7 as we go to 5. Use the limit rules to find the following. The limit of f of x minus g of x is what? Follows the rules you would expect it to follow.
3.
Yeah.
So this would just be 4.
Mm-hmm. Okay, when you're looking at limits of rational quotients, in other words, a polynomial divided by another polynomial, they're only difficult if upon direct substitution you end up with 0 over 0. By that I mean, if I want to know what the limit of x over 3 is as x goes to 5, it's 5/3. In other words, direct substitution, but what is it as x goes to 0?
That'd be 0.
Okay, and as x goes to infinity, the limit is infinity. But if we look at this, whoops, excuse me, I meant to reverse that. What's the limit as x goes to 0?
I can't see the bottom part of it. Did you do a 1 or a 3?
Wow. Here, I'll try to move it down. I know what I can do. Is that better?
Yeah, right there.
What's the limit of 3 divided by x as x goes to 0?
It'd have to be 0, right?
0, right?
Infinity.
Oh, okay.
Oh.
Notice what happens if I have 3 divided by 1, that's equal to 3. But if I have 3 divided by 1/10, that's equal to 30. And if I have 3 divided by 1/100th, that's equal to 300. So it's all I have to do to make this a bigger number is to make this smaller. So as I approach 0 in the denominator, my entire value is going to blow up, going to get larger. So the easy parts of limits are where either the denominator or the numerator blows up. The tough part of limits is when direct substitution results in 0 divided by 0. Notice that, let's see if I can put both of these on the screen. If I substitute 5 for x, the denominator is 0 for sure. What's the numerator? The numerator is 25 plus 20 minus 45. So this is a 0 over 0. That's the limits that are hard to evaluate.
Okay.
So there's 4 or 5 techniques to use when you get 0 over 0. If you get anything other than 0 over 0, well, infinity over infinity is also hard to evaluate. We don't know what that is. But anything else, we know what it is. If I get some number, 4 over 0, that goes to infinity. And if I get 0 over some number, 6, that goes to 0. So all limits are easy except the ones where you get 0 over 0. So that's what this is. So one of the solutions, the most common one, is to factor. So factor the top for me. Can you see? Yeah, you should be able to see that.
Yeah, I can see it.
Okay. What's the top factor?
Plus 9.
And the bottom, what's this called?
Perfect square.
Well, it's called the difference of perfect squares. But
So it's x
in
plus 5, x minus 5.
yeah, in calculus, it doesn't have to be perfect anymore. In other words, if I said factor this, guess what? That's equal to square root of x minus square root of 7 times square root of x plus square root of 7. In other words, I can factor any two terms using the difference of squares, even if they're not perfect squares. Every number is the square of something. 7 is the square of square root of 7. And this will come into play. You'll get limit problems that require you to use this, or at least this is one of the easier techniques. Don't need to use it here, because now I can cancel this x minus 5 with this x minus 5, and I'm left now with x plus 9 over x plus 5. And now when I go to evaluate this limit, it's not going to be 0 over 0 anymore. It's going to be 14 over 10. There's the limit.
Oh, so you substitute it straight in.
Yep. In other words, once you've canceled what you can cancel after you factor, you'll be able to substitute straight in and come up with a number.
Okay.
Okay, so that is 7 divided by 5, like that. Yeah. Okay, another polynomial. Hold on. I move this. I'm going to try to write in. Gosh, I wonder if I've had this problem with all students and nobody has bothered to tell me that they can't see when I'm writing.
No, I think what it was, the zoom button, I hit full screen instead of scale to fit. So
okay.
It only took like a portion of your screen, but
Okay.
it was all of mine.
Okay, now here we're taking the limit as x approaches infinity. Well, if we do a direct substitution, we have infinity over infinity. So that doesn't do much good. So when x approaches infinity and you have a polynomial over a polynomial, I could try factoring. But I can see right now that this bottom does not factor nicely. There's no way it could. I could have 3x and 3x, but then what am I going to have? I'm going to have minus 1, and I would have a middle term of 6 minus 6x. So the bottom does not factor nicely. However, what I can now do is divide every term in the top and bottom by x squared, the highest degree there is. So here's what I'm going to do. I'm going to take 5 by the highest degree in either the bottom or the top. So I'm going to take this term, divide it by x squared. And I can do that as long as I take every term and divide it by x squared. So this becomes this. Agreed that we can do that?
Yeah.
Okay, what happens is those cancel. That cancels with that. Those cancel. This becomes 1 over x, and this becomes 1 over x squared. Now, as x goes to infinity, all of these terms that have an x in the denominator go to 0. In other words, this one goes to 0, this one goes to 0, this one goes to 0. The only thing we have left is 5 over 9. Notice that we could have saved ourselves a lot of trouble by just checking the highest degree variable, which is x squared in the numerator and the denominator, ignoring everything else and taking the ratio of their coefficients, in the same way that we would be looking for a horizontal asymptote. Remember how you find a horizontal asymptote? You take the ratio of the coefficients if they both have the same degree of x. And also, when we're looking at x going to infinity, we're looking at end behavior. And in end behavior, the only polynomial that makes any effect is the largest one. you can effectively ignore all the others. In other words, the shortcut to this is, well, I noticed that that's an x squared, this is an x squared, the limit is 5/9.
So you can just straight up just look at it and know.
As long as those are the same degree. If this one is
okay.
x and this one's x squared, you can't do that.
Okay.
I can still go through that process that I did, which is to divide every single term by the highest degree, which was x squared. That's always a legitimate thing to do. You can divide the numerator and the denominator by the same thing no matter what it is. Okay, so this is 5/9. Okay, so now look at this carefully. In other words, they're not always going to come with the term on the left being the highest degree in this function. I actually have
this one be infinity?
Yeah, it's essentially this problem here. I'm going to ignore everything but that in the numerator, and I'm going to ignore everything but this in the denominator. Well, now the x squareds cancel, and I'm left with an x squared up there. What's the limit of that as x goes to infinity?
Well, if it's 8x squared over 5 infinity.
This negative sign is going to matter. What is the limit of this? Well, let's start with the basic. The limit of x is infinity. What's the limit of x squared?
Infinity.
What's the limit of minus x squared?
Infinity.
Negative infinity.
Even though it's the squared?
Because this square is not operating on the negative sign. It's only operating on the x. Just like this square here is only operating on the x, it's not operating on this negative sign. So the negative sign does not disappear, unless, of course, it's this. If I'd have said this, that is positive infinity, because a negative times a negative is positive. But if that negative is not being operated on by the exponent, then this goes to negative infinity. Now, I got to ask you a question. Does your class, hopefully they do, distinguish between infinity, negative infinity, and does not exist?
I do not know.
Well, we'll find out real quick here. In other words, I would put negative infinity. Let's see if that gives us the right answer here. Let's see, there's my negative sign, and then I push this infinity key over here. Is that correct? Okay. Okay, so negative infinity was correct. Since we're talking about that, let's look at a different situation that really clarifies it. What's the limit of that function at x equals 0? What's the limit of y as x goes to 0?
Well, it could be negative infinity or infinity.
What is it coming from the right?
Infinity.
What is it coming from the left?
Negative infinity.
Since they do not equal one another, this has to be a does not exist.
Oh, okay.
Okay.
That makes sense.
Let me change the function slightly. I'm going to make it 1 over x squared. Now what is the limit of this function as we approach from the right?
Infinity.
And from the left?
Infinity.
Since they are the same, this is infinity. In other words, infinity and does not exist are not the same thing.
Okay.
And a lot of math courses will kind of teach you that they are the same thing. In other words, whenever you run into the number infinity, does not exist is the same thing, but it's not. And this is the perfect illustration of why it isn't. All right, let's go to the next one here.
So is this just solve for t?
Well, notice that if we substitute infinity for t, we have infinity over infinity. But notice that t is just a variable, just like x was in the last problem. What is our highest degree variable in the numerator?
T.
What is it in the denominator?
T.
What's the ratio of their coefficients?
3,500 over 5.
3,500 over 1.
So it'd just be 3,500.
Okay, which of these statements is correct? The number of tumor cells gets closer to 3,500 as the time increases. Well, that's kind of what this says. As the time increases, we're going to approach 3,500.
So it'd be C.
Well, what is it? I thought A said that. One says as time decreases, the other says as time increases.
So it's as time increases.
Yeah, so you're right. It should be C, huh? I guess we got to go to 10 next. Yeah.
I'm not even sure how to go about this one.
Well, here's the equation. Let's write this equation. Let me move this to the left. Can you still see that equation? P of n? Let me not cover it up. There. Now you can see it. Okay. So P of n is equal to 1/2 plus P sub 0 minus 1/2 times 1 minus 2p raised to the n power. So they're asking interpret p sub 2. So they want to know p sub 2. Well, which means that wherever we see an n, we're going to fill in 2. P sub 0 means the first one. Find and interpret P sub 2. Okay. Notice that there is a P sub 3 also. Well, P sub 3 is just substituting 3 for n. P sub 0 they've given us. P sub 0 is equal to 0.78. Right there?
Uh-huh. And then P right there.
And P is 12.12, excuse me. So we should be able to substitute everything in for that. So P sub 2 equals 1/2 plus 0.78 minus 1/2 times 1 minus 0.24 squared. Do you have a way to, do you have a calculator in front of you? Let's see what I can do here. That's 0.28 times 0.76 squared. If we can get an answer for that and round it to 3 decimal places, we'll have our answer. See, this is really a question about arithmetic or sequences and series. This is not really a calculus question.
So I got 0.6617.
0.662, right?
Yeah.
Uh-oh, you didn't like it. Or did I not click it? Oh, yes, I did. Okay.
All right.
Was that 10? No. It's not doing anything. When I click on question 10, Sean, it doesn't do anything. Should I click on this right arrow?
Yeah, I'm seeing that. I don't know what's going on. Try hitting continue right down at the bottom. Oh.
Oh, there was more to that question. Okay, so now we want the probability that a legislator will vote on the second roll call is, well, we just figured it out. On the nth roll call, we just figured out that P sub 2 was 0.662. So why are they asking us that again? I guess we'll just try 0.662. Oh, I see. We have to make sure that, let's back up for a moment, is what it means. Let's see. P sub n, let's see, the probability that the legislator will vote yes is given by P sub 2. So the probability that will vote on the second roll call. Notice the last sentence differs from the first, only that he'll vote in the first one, and the second one he'll vote yes. So it looks like it's C, and this should be 0.662. If I'm interpreting that, the probability that the legislator will vote yes on the nth roll call is that number. We just figured out that number was 0.662. That's got to be it.
They're flipping around the question all.
Well, yeah, I don't know what they're doing here. Probability that they'll vote is 100%.
Yeah. Okay.
Okay. Find and interpret P sub 4. Okay. Well, first of all, let's write out what P sub 4 is. P sub n is that. So what's P sub 4?
1/2 plus 0.78 minus, or times,
This
1
was
minus,
0.76 if I remember right, wasn't it? Yeah, in other words, P was 0.12. So 2 times P was 0.24. 1 minus 0.24 was 0.76. So there is P sub 4, if you can get a number for that.
oh, I got mixed up here.
Can you see this on my whiteboard? So it should be 1/2 plus 0.28 times 0.76 cubed.
Why is it cubed?
Because it's to the 4th, excuse me. Good catch.
Alright, there we go. I'm just writing this out so I have all the notes for the test. Alright.
This should be a number slightly less than this number, because as you take these to powers, they get smaller.
Okay, so I got 0.593. Alright.
Now I bet we can go to 10, huh? Yeah.
No, it still says continue.
Oh, that's right. Yeah, no, I catch on eventually. Huh?
And then I think it's
That's the same thing.
593.
Yeah. It's weird that they have you put the number in again. Find and interpret P sub 8.
Wow.
Yeah, they're a bit excessive here and making us do all this arithmetic, but it's just plug in. That's all it is. So there's the P sub n. So let's see. Move this over to there. Should be able to see all of this. P sub 8 equals 1/2 plus what is that, 0.78? What was P sub 0?
Yes.
Was
0.28.
0.28. Oh, okay. And this was 0.76 to the 8th power now. So this should be an even smaller number, but still greater than 1/2.
.531.
This seems a little lazy to me.
Yeah, this is
Doesn't it
they
seem
usually
that way
don't
to
do
you
this.
too? Sounds like somebody
Yeah.
ran out of the creative energy to come up with different kinds of problems. So from everything we just looked at, what do you suppose the limit of p sub n is as n goes to infinity?
So as n goes to infinity, p approaches 0.5.
Yes. Because notice that this kept getting smaller. Because this number was 0.76, every time if I squared it, it got smaller, but if I took it to the fourth power, it got smaller still, and if I took it to the eighth power, smaller still. So as n goes to infinity, this thing's going to 0. And now the only thing you have is the 1/2 that's here.
Oh my gosh.
I know.
So I think it's a 0.5.
It's scary when I push it and it doesn't take. Oh, now they want to give us a similar exercise, like they just didn't give us 5 in a row that were similar.
Oh no, we
Oh,
can. That's only if you got it wrong.
oh, I see. Okay. So what should we go to next?
If you click on one of the arrows up there.
Okay. This must be 11 that they put up there. Okay, so where is this function discontinuous?
It'd be negative 2 and 1.
Correct.
I'll be honest, those were a guess because of the points not being filled in. Is that the best way to think about it?
Well, let's go back and look at it again. If you think of continuity as where you have to pick your pencil up, there's only 2 places where I have to pick my pencil up. If I'm drawing this graph, I'm going to draw it. I can draw it, but right here I got to pick my pencil up to make this dot, and then lift it back down again and draw it, and then pick it back up again and finish drawing it. So just think of it as the only 2 points where you have to lift your pencil.
Okay.
Okay? There is a more mathematical correct definition of continuity, but and there's 3 conditions on it. That pretty much is the limit from the left and the right have to be the same, and the function has to exist at that number also. But the pragmatic definition of continuity is lifting your pencil up.
All right.
So what was that? What was it again? Minus 2 and 1?
2 and 1.
Okay, which of the graphs, are we seeing all of them?
Yeah.
We must be seeing them. There's just 3 to choose from. Does the left graph fit the top line of the piecewise function? Does A fit that?
No.
Why not?
The x is less than -1.
That would have had to been a less than or equal to match the closed dot. In other words, the moment you see a closed dot in that, it doesn't match that. It would have to have been x is less than or equal to, so we can rule that out just from the top line.
Okay.
However, this one has promise. It's got an open dot, so that fits the top line. Now, B.
C has one.
No, it doesn't, does it? C isn't a function, notice. C does not pass the vertical line test. So we know it's going to be this one, but let's check the rest of it out. In other words, it should be a parabola between -1 and 3 inclusive. And it is a parabola that's been shifted down by 3 units, which is exactly what x squared minus 3 should be. It is a parabola with its vertex right there. And it's got a closed dot there, and it's got continuity there. So this part fits the middle part, and then greater than 3, it's always equal to 6. The function is discontinuous where?
That would be x equals 1. Or no, excuse me, -1.
Okay. Find the limit of this function as x approaches the values found in part B from the left. So as we approach -1 from the left, what are we approaching on the vertical axis?
It's just, I can't see the graph anymore. I think it's just 6, right?
Yes, it is. Oh, excuse me. Yeah. Oh, they've got this thing broken up so you can scroll just the lower half. Yeah, in other words, if I'm looking to approach this point, -1, from the left, then I'm going to go to the left of it and then move to the right. That's the way to think about it, is I want to go somewhere to the left of that 1 on the x-axis, put my cursor on the function, the graph of it, and move towards the right, towards that point. Well, everywhere I'm headed is 6. 6, 6, 6, 6. So there was only one value we had, wasn't there?
Yeah.
From part
I think
B?
they're just doing that to make sure you knew it.
Okay. And then find the limit as it approaches the value in part B from the right. So here's the -1 that we're going to approach. Since we have to approach it from the right, we got to go to the right and then come backwards at it. What am I approaching?
-1.
-2. Oh, no. No, you're right. It is -1. Why was I reading that wrong? Uh-oh. We're approaching -1 from the right.
Do you think it would be 6 again?
Now hold on. Let me look at the function. Oh, it's -2. In other words, we're approaching -1 from the right, but the y value is -2.
Oh, it's the lowest point?
No,
Oh,
it's
no.
whatever it's going to be. In other words, if I put my cursor right on that point, and I can do that kind of because it's a closed dot, well, what's the y value at that point?
That's
Minus,
-2.
-2. Yeah, if I plug in -1 for x, I get 1 minus 3 and -2. I just looked at it wrong when I did it the first time.
So will you ever use the x value? So for these,
No, the x value is just for determining what vertical line you're approaching, essentially.
okay, I see what you're saying.
Okay. Okay, so let's see, where are we at? Going to the next question, I guess.
Yep. So this,
So, first of all, even though the top factors into x minus 8 times x plus 8, and it appears that we could cancel out the x minus 8's, leaving us with f of x is equal to x plus 8. That has no discontinuity. That would be that line. But just because we have canceled these out does not eliminate the discontinuity in this function. In other words, you have to go back to the original function, and where is this thing going to have a vertical asymptote?
8.
Right, but that vertical asymptote is no longer a vertical asymptote, it's a hole. In other words, if I plot this x plus 8, I've got to put a hole right there at x equal 8. Which means it's discontinuous at x equal 8. Now, here's the odd thing, is that if you graph this function in your calculator, you won't see that hole. You won't see that discontinuity. And the reason is because if you think about it, this thing has to be infinitesimally small. 8 is just one number on a number line of infinite numbers between 7 and 8. So a hole doesn't show up as a hole on a graphing calculator. It shows up as a very, very tiny hole that you have no chance of seeing. But if you'll remember from pre-calculus, this has a hole at 8, which makes it discontinuous. I would not be able to draw this continuously. I'd have to pick up my pencil to go over that hole and then put it back down again. Okay. What is the limit as we approach 8?
Infinity?
No, let's look at this. In other words, if I'm saying this is f of x up here, now I can go ahead and cancel the x minus 8 with the x minus 8. I can do that as long as I preserve the hole. So this function is x plus 8. So as we approach the number 8, what are we approaching on the y-axis?
8?
Plug in 8 for x. What are you approaching? 16.
Oh.
This hole occurs at a y value of 16.
And how'd you get that one again?
Well, I started with the original function. I factored it, the numerator, and I canceled that with that, leaving f of x was equal to x plus 8. So what is the limit of x plus 8 as you approach 8? 16. In other words, you just substitute 8 for x. 8 plus 8 is 16.
Oh, okay.
And the limit does exist because we approach 16 from the left and we approach 16 from the right. So the limit as x approaches 8 is indeed 16. It's just that f of 8 does not exist. In other words, if I said, what is f of 8? Well, there's a big hole there. It's DNS. DNE, rather. Does not exist. They'll probably ask that before we're done with this question, is my guess. No, I guess we're done with it.
Yeah.
Okay.
So it'd be x greater than 3.
Well,
Greater than,
we want
greater
to find if this function is discontinuous. It's not at a equal 3 because that would just be e to the 0, which is 1. So it's not discontinuous there. But notice that whatever's inside the radical has to be positive, so we have to be
it's got to be d then, right?
yeah, that's where x is less than 3. In other words, if x is less than 3, we have a negative number under the radical sign, so that doesn't work. All these other cases are fine. And this one isn't quite right because it's not discontinuous at 3. It's only discontinuous when a is less than 3. The limit as the function approaches the point of discontinuity is what?
I'm not sure. I'm going to guess 0.
Well, let's see. What does it say again? The limit as the function approaches any point of discontinuity, which is to say any number less than 3. As we approach that point, why isn't the answer 1? Because if we plug in 3, we get e to the 0, which is 1. However, if we try graphing this function, e to the square root of x minus 3, it looks much like e to the x, only we're limited. It's going to be translated over. We could kind of model it like this. Something like that. So they're saying as we approach points of discontinuity, which are anything to the left of 3, what does the function do? It doesn't do anything. In other words, if I said, what is this as we approach 0? Well, you can't approach 0. We're not even in the function territory at 0. The function doesn't begin until 3. So 3 is not a point of discontinuity. So the answer here would have to be does not exist.
Okay.
So X is the weight. So we're approaching 3 ounces from the left. What is going to be our charge for postage?
Uh, 81.
So it's going to be 0.31 plus 0.25 for the second ounce. In other words, the first ounce is going to be that. The second ounce is going to be that. And any fraction thereof of a third ounce, which we have, is going to be 0.25. So would you say 0.81?
Yeah.
Looks right to me. Now they're going to say from the right. What's it going to be from the right? If we graph this, notice that it's a piecewise function. If we graph cost versus ounces, up until and including 1, it's 31 cents.
So is it 87?
It's 81 plus 25, 0.25, so it should be 1.06. In other words, here's what this function looks like. For anything above 1 ounce, it's 56 cents charge. For anything between 2 and 3 ounces, it's 81 cents charged. And for anything between 3 and 4 ounces, it's $1.06. So if I'm approaching 3 on the x-axis from the right, I'm up here. That's the only place the function is up there. So as I'm approaching it from the right, honing in on this point, that's 106. You see why?
I'm kind of confused how you got 56.
Okay. The charge is 31 cents for the first ounce.
Oh, hold on. I got it.
25 cents for each additional ounce. So this step function, which is exactly what it is, it's actually a pretty good application of where a step function is used in real life. Well, with postage or with the age of people in grade school.
Okay.
If you're between 6 and 7 years old, you're in this class. If you're between 7 and 8 years old, you're in this class. So, similar situation. So when you look at it graphically, it becomes much more obvious why approaching from the right is 106 and approaching from the left is 0.81.
Okay.
So the limit as x approaches 3 is what?
Is it, I can't see the graph, is it 61?
Well, remember the most important thing about limits at a specific number is they only exist if the limit from the left is the same as the limit from the right. And the
Does not
limit from the
exist.
left was 81. The limit from the right was 106. So this one does not exist.
Okay.
And find C of 3. What is C of 3?
81.
Mm-hmm. Find all values on the interval 0 to 4 where the function is discontinuous.
That's 1, 2, 3, 4.
Just 1, 2, and 3. Now, they use parentheses here, not brackets.
Okay, so it's not included.
Well, I'm not sure, to be honest. Let's try 1, 2. Is it important? Does your grade have anything to do with our performance on this thing?
It does, but it'll be like less than a third of the points for this one question.
Okay. If I were to finish graphing this, the next step would be up here. So 4 would be a point of discontinuity if it was in our interval. So it's important, and in fact 0 would also be a point of discontinuity. No, it wouldn't. 0 would not, because we don't go to the left of that. There is no graph to the left. So it's continuous at 0. It certainly is not at 1, 2, 3, and 4. The only question is whether 4 is in our interval or not. Should we put it in or leave it out?
I think we'll get 2 chances, so we can try that one first.
Okay, I guess these parentheses were accurate. In other words, if they were brackets, then we would have had to include 4, but not 0.
Okay.
Oh, this is kind of nice. Which one of these is what we just graphed?
C. No, D.
It's the only one that has the closed loop on the right. No, it isn't. These do too, but it's the only one going in the right direction. So how would we answer the first question here?
Did you plug 22 in to one of the equations?
Which one?
Either, right?
No. Notice that it's equal to this equation if t is between 0 and 28. But it's equal to this equation if t is greater than 28. And less than 28.
Okay.
So we want to
See if
plug it
it's
into
top.
this equation, the top equation only.
Okay.
And you want to plug 22 in.
That's 0.6549.
0.6549, so 0.6 Round to the nearest integer.
Oh, no, I was trying to read the question still. Alright, now I'm plugging it in.
So it must be above 42. So it's going to be 42 and a tiny bit. Oh, not so tiny. I guess when we square 22 and cube it, we get pretty big numbers.
This is a weird one to plug in the calculator.
Yeah, I imagine it is. Is it any easier to do on the side over here on the left? What do? You write a function on your calculator and then just plug in a value for t and say, give me the value, or do you actually 42 plus 2.88 times 22 plus 0.6549 times 22 squared?
Yeah, I have to do all that.
Okay.
I'm going to syntax error, so I'm going to do it piece by piece then.
Okay. Well, yeah, it's going to be a lot more than 42. .88 times 22 has got to be 50, so it's at least 92 plus quite a bit more. The last term's not going to contribute much, but this term probably will. Now make sure when you do it the way you're doing it now, you don't round off early. You would accumulate round off error if you did. And we may not get the correct answer. We could be off by 1 or more.
So it's in grams, so I don't think this is that bad. 496.65.
So round that off to the nearest integer.
497.
Is this continuous?
Yes, because it includes 28, right?
Well, what if it were to look like this? How do we know it doesn't look something like this? Here's the 28 mark on the t-axis. Here's 56. So I know the function it grows, and closed dot at 28. But then what if this second function, that's linear,
Oh, yeah, it could be above it.
or below it? What if it does something like that? Then it wouldn't be continuous. So how do we figure out if it's continuous or not? Without graphing it. What if we check 28? In other words, if we plug in 28 and we get a value for right there, and we get exactly the same value in the second, then the second one must come off of the first one in some manner like that. So the key would be to check 28 and see if these two things are equal.
Okay.
Now, it's 7:30, so that's probably
I can.
That's quite a bit of work to do, because you got to plug in 28 up here, and then you got the second part's pretty easy to plug in 28 here and come up with an answer. But if they are not the same, then it's not continuous. If they're the same, it's continuous.
Okay.
Okay? So let's see, what's the best way to leave this without screwing you up here?
So if you could just hit save.
Okay, without answering,
Yeah.
then it's going to let you go back to this problem, 16?
Yeah.
Okay.
And
You have
just hit
not
yes.
completed a question. You will receive credit only for the work you've done. Okay.
But I can go back to it. It's fine.
Okay. All right. That works pretty good. I have another student that uses this same system. Only he was in pre-calc.
Oh, okay.
In fact, I think he went to the same. You went to Rock Canyon, right?
Yeah.
Yeah. No, this is a Rock Canyon student, and every time I meet with him at the library, he brings out his laptop, and we go to that page we were just on for pre-calc instead of calc. But similar kind of system.
Gotcha. And then are you still on the PayPal account, the same one?
I am.
Okay.
Yeah, and
And
this would be $48. In other words, 32 per hour times 1.5 is 48. You need that?
Right.
You have my email address? Because my email address is my account name at PayPal.
Okay. Yeah, if I could just get that one more time, please.
I'll write it here. David Cowan with an A, 1949 at gmail.com.
Okay. And then next Tuesday, we won't need to meet. I'm actually going to be in the Dominican Republic for vacation, so
Oh, cool.
no internet access there.
Okay. You know, you can schedule online if you like, or I'd be happy to schedule while we're on the phone now. Is it always a Tuesday session you're going to be looking for?
Yeah, Tuesdays are okay.
You want me to put you down for the first week in July on that Tuesday?
Yes, please.
You want an hour and a half or hour? Or 2 hours?
We'll go with an hour and a half again because the homeworks usually tend to be about this size.
Okay. Yeah. Sounds good. You're down for July 2nd. And on July 2nd, I will just text you the meeting ID number since you're all set up.
Okay.
Okay?
All right. Thank you so much, David.
Yeah, good working with you again, and I'll talk to you in a couple weeks.
All right. Have a good one.
You too. Bye-bye.
Bye.